Well, thank you so much. And I really appreciate being able to follow Lisa and as she talks about understanding what exposures are. And that's what I'd like to present today on some of the work that I've been doing in order to develop new tools that we're able to better understand what our exposures are, especially to respiratory viruses, including SARS-CoV-2. So being able to track infections using virus surveillance has really allowed us to go beyond just recognizing where infections are, but understanding just how it tracks across a larger scale and also understanding the risk of different environments. And being able to monitor what our exposures are within the air, given that we have this airborne virus, presents some challenges in how we're able to do that just because of the levels in which we are trying to assess and the challenges with being able to quantify incredibly low levels. So this means that we can't use conventional technologies that require hundreds to thousands of different copies. And so we're left looking with other solutions that will have increased sensitivity. Different methods in which you could evaluate exposures in different settings have really relied on use of surface swabs or use of different active aerosol samplers. So there are challenges with both. If we rely on being able to look at just surfaces and deposition, we might just be missing different points in which we are exposed. Use of active aerosol samplers limits us to only looking at areas in which we spend some of our time. And if we think at occupational exposures or even environmental exposures, we move place to place. We can't limit ourselves to one environment. In addition to all the other caveats with area samplers and active samplers that draw air using a pump through a filter, they're loud, they're expensive, and they certainly cannot be worn. So in order to overcome a lot of these issues, my work's focused on being able to look at wearable technologies. And I have a little guest here who in the course of the pandemic has also learned a lot about exposures. So we've developed a wearable technology that we've called the Fresh Air Clip that passively collects respiratory virus onto a silicone surface and doesn't use any electronics to be able to do so. So this has now allowed us to personalize air monitoring that we can look at early warning signs for transmission risk using this technology. To support a lot of this work, we originally started by deploying some of these surfaces across COVID's infection positive wards within hospitals in the early phase of the pandemic. And we hung samplers over top of where patients were lying within their beds, shown over here in the figure here in this blue box here. And we also put a little picture frame with a passive sampler, so just a silicone film on their bed table. And with both of these samplers in every room that we went to, we were able to then pick up this COVID's or the SARS-CoV-2 laden virus or droplets. So this really then set the precedence to say that we could now have a wearable type of device that used the same type of diffusion-based passive sampling. So with this, we took a polymer film and were able to then have a passive uptake of virus-laden aerosols. And by doing that hospital-based sampling, we're able to demonstrate that passive sampling could effectively uptake these airborne viruses. We were then able to demonstrate that we could effectively extract the deposited virus off these surfaces with consistency within our recoveries, and also have good sensitivity in terms of the number of RNA copies that we could detect per clip using a digital droplet PCR technique. And then to be able to make a conversion between what was collected on a sampler to what actually the exposure was, we were able to then measure what the uptake rate of aerosol was onto a passive sampler. And so this involved being able to have a steady state environment where we could inject a known concentration of similar sized particles as we would assume that particles associated with the virus would be, and then allow for sampling over extended durations. And looking at that rate of uptake of those virus-laden aerosols onto this surface, we could then use that to then estimate what the number of RNA copies that someone was exposed to in a 1 cubic meter volume, and then express that concentration in RNA copies per cubic meter. And once we're able to have this technology from measurement to exposure estimates, we then deployed those in a range of different environments to be able to use this as an exposure assessment tool. We were able to use it, and we have now expanded the use beyond the study that I'll show you right now, is deploying it over the course of about a 6-month period in the Connecticut area with healthcare workers, but then also other environments that people would frequent and wouldn't have PPE on, including restaurants. We looked at different homeless shelters, as well as just general community members going about their daily routine. And we were able to then look at what the exposures were in each one of these facilities or areas. Overall, we detected an 8% detection of SARS-CoV-2 using these wearables for these different settings. And we were able to then find airborne levels of SARS-CoV-2 in these different areas that range from 4 to over 100 RNA copies per cubic meter. Most frequently, we found that the virus was detected for restaurant workers, but we certainly also found it for other areas as well. And that's shown over here in this violin plot, looking at these concentrations on a log scale here. And the levels that we were seeing in the bottom were shown in relation to other reported levels. So what's next with this research? So we're now looking to see how exposure of respiratory virus that we are exposed to, that we are potentially inhaling, and then relates to the detection of COVID infection. So we're pairing all of these wearables with collection of saliva and being able to then measure what the relationship is between exposure and then conversion into infection. So we're excited to be looking at this in a number of different daycare settings in the New Haven area. And then further, this work has really then presented other opportunities to be able to look at other respiratory viruses. And we're doing that with a full panel of other common respiratory viruses in addition to SARS-CoV-2. And then further pairing that with chemical exposures that we know that can potentially increase sensitivity to infection as well as severity. So with that, I'll stop there and just thank the wonderful people that I've been able to work with on this project, and then also leave you with this paper here that goes into more detail with this technology.